Good afternoon. My name's David Holzer, one of the senior fellows with SANS Institute, and also one of the instructors for the Secure Coding in C and C++, actually the author of the class, in addition to being an instructor for many of the other classes that SANS offers. What I wanted to do today is take a few minutes and create a three-part webcast here for you that will help you see how to go about finding vulnerabilities, how to create an exploit by hand, and then finally, how to turn that into something that you can use in Metasploit. Let's get started right away. We've got a short slide presentation here, and we're going to switch back and forth between this and the an actual virtual machine where we've got some code, some vulnerable code, where we can do some experimentation and see how it is that these exploits come about. First of all, let's get right into the material, how overflows happen. It's really a very, very simple concept. There's two main kinds of overflows that can occur. We're either going to be dealing with some kind of a stack overflow. This will almost always have to do with an argument that has been passed on the stack, or perhaps a local variable within a function, and we end up with an unbounded write. In other words, we're able to write past the end of a buffer and create a stack overflow, because the local variables within a function, and any, of course, arguments that are passed to a function, are all passed on the stack. So if we can push past the end of a boundary of one of those buffers, we end up with doing what's called smashing the stack, or messing with the stack frame pointers, essentially. The other kind is a heap overflow. Heap overflows tend to occur either with global variables, or perhaps if we're dealing with dynamically allocated memory. We're not going to focus on heap overflows in this particular concept here. We're just going to take a look at stack overflows, because in essence, they're easier to exploit, or at least easier to demonstrate. Stack overflows, like we said, take advantage of this idea of argument passing. To have a clear picture of what's happening, you need to understand how it is that arguments are passed in, to, and back from a C program. Now we're focusing here on C, not because stack overflows can't be done in anything else, but because most types of languages today actually take advantage of C-style argument passing. Now, the other main way of passing arguments is the Pascal method. This just has to do with the order that things are put onto the stack and taken off of the stack. Of course, it would be possible for someone to create their own method of passing arguments if they were going to implement their own compiler. It's going to turn whatever the source code is into assembler. However, the C style is a standard that's used by most languages today. Again, we said that this is going to affect argument passing, but also any locally defined buffers within a function. So if we define a variable that's used within a function, you may remember in C that that function or that variable is only in scope or available while you're in that function. There's a very, very simple reason for that. The reason is that variable is actually stored on the stack. So as soon as we come out of that function, the stack frame is returned to its original calling position before the function was actually entered, which means that that variable, even though its content is still there in memory, is no longer available because the stack frame pointer has been changed. We can't find that data anymore. Let's take a look at some pictures that may help us. Now the pictures here we've used, and we can see that there's an annotation at the bottom. These are actually on Wikipedia. We've got some very, very nice illustrations there. These are available for free use, so we've chosen to use them here. And they follow the same type of illustration that you typically find when talking about buffer overflows, or an illustration of memory or a stack. There is something that makes it a little difficult looking at this, because if you look at it, it's very important to notice where things are. For instance, you notice that the arrow on the right-hand side of the diagram, this one over here, says that the memory addresses are going, well, they're going up, but in which direction? The memory addresses get larger as you move toward the bottom of the picture. And that may seem counterintuitive, but the reason for that is, if you were to dump out memory from let's say a debugger or something like that, you typically find that higher memory addresses are toward the bottom. Now there's another interesting thing over here, very, very important. It says that the stack grows in this direction. In other words, when your program begins executing and the stack frame is originally created, the stack is going to be at the top of the program memory. And as things are added to the stack pointer is actually moved down in memory accounting for the difference in space. So let's say we're going to push a 4-byte value. Well, the stack pointer will be reduced by 4 bytes. So you can see in this particular case, a function has been called, and that's actually what we're seeing here. We can see that up here, the parent routine stack, we don't know what's on that stack. It's really none of our business. Our function has been called, and within our function, there are several things that are pushed onto the stack. We find the return address of where we're going to come back to. We find a saved frame pointer that's going to be where to return the stack pointer to when we exit this function. And then we have locally allocated variables. So if there were any arguments that were sent, they would actually appear before the return address, and the variables that appear after the saved frame pointer, or literally in memory before the saved frame pointer, these are locally allocated variables. So you can see here that we've got two variables. We've got a pointer called bar, and we've got this character array called C, and that has 12 different slots in it. Well, if you take a look at this next slide here, let's take a look at using this particular call stack. And we can see in this case that the local variable C, that array, has had several bytes of data put into it. Now, there's some errors that are made when we're writing code, and this particular material comes out of our secure coding class for C. For instance, you notice here the word hello. A very, very common coding error is to only take into account the actual letters that make up a character buffer. But when we're dealing with character strings in C or C++, we're almost always dealing with null-terminated byte strings. That means that the length of this string is not 5 characters, which is actually even what the strlen would return if you were to run that function on this, but the actual size is 6 characters, because we must also take into account that null. You can see how it would be very easy to put 12 actual characters in here and then end up with a null added onto the end, which could potentially overwrite part of the bar pointer. Well, that's when we have normal data. What would a buffer overflow look like? Well, that's very, very easy. A buffer overflow would simply mean that someone has sent more data than fits into that variable. Now, how that data gets in there, that can happen a lot of different ways. It could be because we're getting some data from a user and they're entering it into the console. It could be that we've received network data that's misformatted. It could be we've read a file off the disk. Whatever the case may be, we now have an unbounded write. And you can see in this case that the uppercase letter A has been sent, and more than enough of them. In fact, let's see, we have 4, 8, 12, 16, 20 capital letter A's that have been sent, and they overflow out of the C array into the bar pointer and then over the stack frame pointer. And then finally, notice the value that's been put here in this red section. This red section was originally the return address, but now that has been overridden. So we can choose to put an arbitrary value into the return address. And this is important because the instruction pointer itself cannot be directly manipulated. In other words, we can't choose to move something into EIP. And the instruction pointer is how it knows what code it's actually executing right now. But if we put it into the value that the return pointer will use, when this gets popped off of the stack into the instruction pointer, it will then redirect execution back to the beginning of our buffer. Notice the address here. And please notice that we've taken that address and put it here into the return pointer. Now, if you're somewhat new to looking at this, you may notice that this number does not look exactly like this address. In fact, if you look at it, you'll notice that it's written more or less backwards. Here we have the 80C03508. That's because of how numbers are stored in Intel architectures, which is the kind we're looking at here. And while buffer overflows can be accomplished in other architectures, Intel architectures are the most common to find people writing exploits for. So that's how a stack overflow works. What about a heap overflow? Well, the concept is very, very similar. Essentially, we're just going to have a buffer of some kind. This could be a memory pointer, it could be an allocated array, it could be a function pointer, something where we're going to take input from a user in some way, over the network, out of a database, something off a disk. Whatever method that it gets to us in, this data gets pushed into this array or into this memory location, and we end up with an unbounded write. Again, there's many ways this can happen. We go into almost all of them in our secure C and C++ class, but for right now, we're just focused on how it is you go about developing an exploit. With heap overflows, there's a tremendous amount of research going on in this arena because of all of the protections that have been put in place around stack overflows. Though even with the protections, all of the different protections that have been created for stack overflows, there are well-known ways to defeat those protections. So stack overflows still are viable today. But for today, we're not going to talk about heap overflows. We'll just focus on the stack overflows. In our next section of this webcast, we're going to take a look at how you actually go about finding the flaws in these pieces of code.